Welcome back, and we're gonna do last video about springs. This is it. We're finally at the end of the spring saga. Sorry. So we're completely done. That's it. After this video, no more springs. So out of all the work that we've done, from just understanding springs to adding the bones and rotation and position, and in the last video we actually did everything on the GPU. Doing springs on vertices. so now that we actually can do everything on a GPU and make things really fast and very efficient, now we're going to explore that. Before we just moved everything into position to kind of create these little grid terrain that kind of springs into life, that springs up into position. Now we're going to actually really explore things, because now we're going to do soft body physics. And soft body physics is the idea of just basically moving points around, which is usually connected to make meshes. So this way they look like clothing and things like that, things that move, and they stay connected and they're meshed and everything else. But soft body physics, sometimes it's like springs is one of the things you use, one of the options of how to move things around to get them into place. Like certain things that are elastic and they kind of spring back a little bit. Sometimes you can have flesh, and the more flesh you have, I have a big belly, so when I press in, it kind of shakes. You ever seen that scene with The Simpsons where I think Homer Simpson, his belly gets poked by the doctor and he just keeps shaking nonstop, and the doctor's like, "Oh, this is bad." So it's like that. So when you're dealing with soft body physics, springs is one of the tools you can do to kind of help facilitate the movement, to make it slightly realistic. You kind of just trying to simulate trying to simulate it a little bit. Another thing with dealing with soft body physics, like, I'm not an expert, mind you. I'm just right off the bat. I've never did soft physics until I did the things for this tutorial. So I'm really kind of a noob, but what I've come to understand about it is there's a lot of things that comes to it. It's like, this is kind of a primer, just kind of like a starting point for soft body physics for me and for you. But now I lost my train of thought. I just want to put a disclaimer there. I'm not an expert. But oh my god, I totally lost my train of thought. So yeah. So all right, whatever. So soft body physics, and I can't think. I had something I was going to say and I totally forgot. So all right, let's see what we're going to do. We got to do with soft body physics. So it's points, right? So we're going to move them around. Oh yeah, okay, that's right. The point of sometimes, like especially when you're dealing with flesh, is that things move and then you got to move them back into a resting position. So the movement from point A to point B and back to point A again could be done in a lot of different ways. And like I said, springs is one of the tools you can use to do it. And flesh behaves in a springy way because flesh itself is stretchy. It stretches and it stretches right back into its original state. Same thing with Jello. You can use spring body physics to create a little bit of Jello kind of motion. Just not that bad. So, and also another thing to with soft body physics in general, especially when you're dealing with flesh, and in Jello, whatever, there is collision. Sometimes it's collision or interaction with things that causes these vertices to be moved. Some kind of physical force, is it moving against it or with it or whatever? There's some kind of force that's causing those vertices to move, and then they move back. And if you think about it, like we're working with vertices, but you have to look at physically what the world is. We look at flesh, but flesh is made out of cells and made out of atoms. They're all kind of interconnected. They're essentially cells and atoms and fibers. They're all just vertices. It's just real life representation of what vertices are. Vertices are just points in 3D space that connects triangles. And, like I said, cells and atoms and proteins and neutrons and protons and electrons and whatever. They create molecules that bond and make shapes. So you have forces that move it. Like air. air. You give it enough cold temperature, the air molecules will slow down and they get closer and closer and they bunch up. And the colder it is, they start to get really close and they well, I should not air. Well, air does compress in cold air, but like water in general, they things get closer and closer to become water becomes a solid, and once you add some heat to it, the molecules will expand and become liquid form again. And add enough heat to it, water then becomes air. It becomes oxygen and hydrogen. So those vertices are moving and they're moving around and whatever. So yeah, whatever. I'm going too far with this, with the analogies and whatnot. So let's just get to it. So like I said, we're one of the big pieces that we're going to do today is dealing with. We have these vertices that we can move around, but now we need to interact with them, and we need to apply some kind of force to them. Something's moving against them, things like that. So for the first example, we're going to do, like I say, a floor collision. So you have a vertices that move down, they touch the floor, and when the animation is done, it springs the object back, but there's the floor is no longer there. So everything is like all that energy got built up, and then when the energy releases, it kind of just drops and springs. So this is a nice simple example of just applying a little bit of collision detection to an object. And then all that energy gets stored up, and then when you release it, it just springs back into its resting position using spring physics. You're like, well, how does this work? So we're going to skip all this gobbledygook because it's from the last video. This is the exact same page from the last video. I just changed the transfer feedback, the shader. That's it. So I'm not going to teach you how transfer feedback works. If you really care, you got a 40-minute video that I just recorded like 10 minutes ago. So you can watch that again if you really care. So this is the meat and potatoes. We're going to the actual transfer feedback shader that does it. So in here, we're buffers. We got very simple buffers. We're going to pass in the position, our velocity, and our resting position. And our resting position is a read-only buffer because that doesn't change. So that's a read-only, and that's shared between the transfer feedback A and B, right? And we're going to only output our following position and our velocity. Our following position basically is our current position that the vertice exists in. So we're going to take our resting position and add it to our model position. Our model position is basically just the position of the sphere. The sphere is a model. So I'm moving the sphere and I'm moving all the vertices along with it. So this gives me basically kind of like the world position of where the vertice currently is. So where's the vertice currently in world space? So if the y position is less than 0, that means I'm actually below the floor. So what I do is if it's under the floor, first I have to even though I'm not modifying the velocity, I need to save it back into transfer feedback, because if I don't do that, I will lose the data and it just becomes all zeros or just garbage data. So when you do transfer feedback, every out variable has to be saved. Even though you don't use it, you don't compute anything with it, you have to save it right back out. So like I said, at this point, I'm not modifying velocity, but I need to save it back up for the next feedback. The same thing with position. And the only thing I'm doing with positions, I'm fixing it so that it touches the floor. So what it's doing is kind of basically touching the floor in relation to where it currently is. So this way, even though the sphere is dropping down, I'm keeping track of where that vertice needs to be because it's colliding with the floor. So this basically is my entire collision detection. And this is the collision detection. It's detecting that it's something, and this is the result of the collision detection. It's like move it to where it looks like it's not moving past that point. Once the vertice is not being collided with anything, I just run the regular spring physics. So if it's not colliding, it's moving based on its current velocity. So that's why when a thing goes up, it goes into that if statement and it's like, well, you know what? Its current position is not its resting position, so I'm going to move it into resting position using using the spring physics. And there you go. Like I said, you're applying force to vertices, you're building up that energy, and then when that force is gone, you can release it, and that's where the velocity and everything else, because it's that speed to try to get back to its resting position, and that's where the energy comes from. It's that distance between its resting position and its current position creates that energy. And the further away it is, the larger the spring is going to be. If it's really close, the spring is going to be very short. It's going to be a very short spring motion. But the greater the distance, the more emphasized the spring is, and that's what I meant by energy. So that's simple enough, right? That's really simple. So that's not the only example. So this is an example of just simple floor. But now, like I said, we want to deal with flesh, right? So flesh. if you search enough on the internet about like flesh and spring and like soft body physics, you might turn up into something called Poke Abby. It's a video game. If you're under 18, maybe even under 21, I don't know what the age is for porn, to be honest. I'm almost 40 years old, but I said the P word. I'm flagged. It's a game. It is a game, but it's called Poke Abby, and the whole point is you poke this 3D character. But the soft body physics on it is actually pretty good. I read a tutorial, not tutorial. I read an article about what he did with it from a long time. And it's not an article. I think it was like a Tumblr or like a blog post and how he developed it. And essentially, it's kind of like they kind of use a sphere. So if you're let's not beat around the bush, right? Basically, you're poking boobs and you're poking a butt. Right, and those are very fleshy pieces. So if you're like virtually, you're trying to poke it with your finger, right? So if you're pressing into a boob, it's gonna go in, right? It's fleshy. It's very fleshy. There's no muscles, no resistance. It's kind of like a bag of water or a bag of sand. You can, with enough force, your finger will sink into it, or whatever object you want to use, whatever. This turned out really bad, but so the idea is that the fingertip is essentially a sphere, so you can use a sphere as a collision detection. So when I want to move, so basically I want to move a sphere into it and then move the vertices. And now there's just a simple way is to say, well, if this vertice is within the sphere, just move it to kind of like the radius of the sphere. And I did that, and you know what? The results aren't that great. Like, to me, it didn't look realistic enough. The vertices kind of spread out, and it might make sense sometimes, like it spreads out and stretches, but like literally, if you're gonna press into a boob or a butt or whatever, like any fleshy, or my belly, where it's very, very, very fleshy, there is a bit of stretching, but you're more pushing the flesh because there's a lot and not a lot of stretching, depending on how much flesh. So I try to figure out a way to move the vertices in a more realistic, in my mind, more realistic. The points are shifting based on the sphere. And doing that kind of work in GSSL is very difficult because you can't output the numbers that you're getting, and number two, it's hard to debug math in GSSL. Like for me, because I don't have no tools to help me debug that stuff. So I decided to do everything in 2D. So I experimented with 2D first, and so this is actually the results. Like this runs JavaScript and it has all the data and it's running the data, and that's where. This is all real. So if you look at the source code, you'll on what's this called? CodePen. You can actually get all the source code for this, which is really easy. So you see these gray dots. So that's going to be like our vertices, right? And this sphere is going to represent a finger or whatever. It's gonna press into the sphere. So ideally, like if these points will kind of spread out away. So like it's here, so it spreads out. It will end up here. Where I want it, where that green spot is where I really want it to be, not over here. And the further out it is, the more spread out it'll go. So so this point will probably spread out over, like more outward, like here. So everything will spread. Like where these yellow lines, it's basically will just keep going. So like this one's probably more noticeable. It'll end up here. And that's not where I want it. I don't want the spread there. I want it to spread here. So this way, when I look at the vertices, it actually looks like that the shape is being impressed into it, like clay. Like the same idea as clay. I'm pressing, like if your finger's going into clay, there's a bit of stretching, but you're actually making an imprint into it. And that's what I really want. I want to make an imprint. So it took me a while, but I managed to figure out a solution for it. So so the idea is that I know the center of the sphere that or the object I'm interacting with. So, and I know the center point of the sphere I'm going. So I know I have this direction. So I know the direction. So if I take the center of the colliding sphere and the center of my vertices sphere, I know the direction where I want the vertices to move. So that from that point you see that arrow. So that means all these points inside the sphere that's within the sphere inside the moving sphere, they need to go in this direction. That's why I have the yellow line saying going this way. Now the biggest question is, how do I know to move it to that spot? That's tricky, right? So here's the thing. I know the center point of the colliding sphere. I know the current position of the vertice, and I have a general idea of where that point's been. I know that point is going to be moving in that direction. It's supposed to go in there. So I know that direction. That's why I have that with an arrow saying, because I don't know how long that distance is. That distance from this point to the green dot. Can I zoom in more? Because I think it's probably really tiny. It looks like on the screen. There you go. So from this point to this point is kind of an unknown distance. I don't know that distance, right? But here's the thing. From that point to the center, I know this distance. That's known. I know that distance. And here's the beautiful thing. Even though I don't know what this position is, I know how far away it is because this is a circle, right? It's a circle. All distances from the center are equal, essentially. So from here to that unknown point is the radius of the sphere. So from center to the final point, I know that distance. And from here to here, I know that distance. So the only thing that's missing is what is the distance? And I know the direction that I'm moving. I just need to know what's the distance of that travel I need to do. So the only thing that I'm missing is between the green point and its original position. So these 3 points make a triangle. So you can use triangle math to actually solve the answer. So at this point, like I said, I know the lengths of 2 sides of a triangle. It's this third side that I do not know. So I know two of the 3 sides. And since I know what this position is, I'm trying to think. Do I know an angle? I know an angle of some kind. Which angle do I know? I totally forgot. Well, whatever. Once I look at the math, I'll jog my memory where the angle is. But around here somewhere, I know the angle. So I know 2 sides and 1 angle. And when I know 2 sides and 1 angle, someone was very nice to tell me just use the law of sines. So using the law of sines, I was able to take the 2 lengths and 1 angle and solve a third angle. Once I have 2 sides and well, first of all, once I have two angles, I can get the third angle easily. You add the two angles together, and then subtract it from 180, and that gives you the third angle, because a triangle is 180 degrees. So as long as you can solve two angles, you get the third one for free. Bing! So I have two sides and three angles. All that information using the law of sines, I can then use the exact same sorts of equations to actually get the final length from here to here. So essentially, you turn everything into triangles. So by turning everything to triangles, you can then use a lot of that, like the law of sines or the law of cosines, to kind of help you find angles and distance. But you kind of have to know at least three things, like three sides, which you can use the law of cosines. If you know two lengths and one angle, you can use the law of sines. I think you can lose the law of sines. Like you have to know at least one of each. Like two angles on one side, or two sides and one angle. Then you could use the law of sines to solve for the other angles and the other sides that you're missing. So once you figured out that distance, you just take that direction and just move it that much distance away, and boom. So everything kind of. So when this thing presses in, it has the green dots and this. And what I didn't do, but what you can do further is you can have a sphere, and then you can have a sphere of influence on top of that. So you have like two spheres of influence. So that it's another sphere, but that one has like more of a, like where this is more definite. Like the second sphere would be less. So this way, instead of these points touching the circle correctly, it would actually maybe be a little past the circle. So this way, when you, like I say, especially with flesh, if you press your finger into flesh, you see that it's like if you do clay, this is exactly what you're gonna get. Like this is clay. So I'm pressing a sphere into clay, and I'm gonna make that impression. But if you're doing something like Jello or something that's stretchy, like flesh, it's not gonna make an impression. It's gonna have kind of like a bell curve instead of if you use clay, you're gonna get like a cylinder kind of shape out of it. Where if you use like flesh, you're gonna get like a bell curve. Like the edges will kind of bend into the hole. Where here, I'm just making the hole like straight through. Where if I had a second sphere of influence that's like the further away, the less influence it has, I can kind of start moving these things into it, making more like a bell curve of type of like impression. Like put your finger, like if you have a big bell, then press in, and you kind of see what I'm talking about. But it's a bell curve essentially, type of, not the equation, but the shape. You have that. I always feel like I have to show it because images. Yeah. Like this, but up backwards. Like if the sphere is going in, so you have this like little tapering. So, like I said, you have the one sphere influence, which does the main push, and then second one. Actually, you could probably do it all in one, for all I know. I haven't really sat down to really think about it, but you probably can have in like the further away, or actually the further the angle. So if that's a dead center, and the further the angle is, like I guess you can use like a dot. Yeah, you could use like a dot product. Yeah, you can use a dot product. And the further away is the more influence or less influence that you get. So there you go. So yeah, if you're like within a certain angle or whatever, maybe that might work. I don't know, but you can experiment with it. But that's if you're trying to mimic flesh or Jello or like anything stretchy. Let's see. So sphere collision, like I said, everything's the same except for the shader. So let's see what we got in here. So we got the same stuff. I have the ball center. And so I pass in, I get the angle, Vectors must be normalized. Okay. Law of sines. This is A, B, B, and you get C. So I know two angles? No. Let's see. In case you don't know what the law of sines are, 'cause I kind of do and I kind of don't. So, law of sines. That's why I kind of write the name like that, because the lengths are lowercase and the angles are capital. Is there a better example? Yeah, there's like this one. So like you have B, capital C, capital A, but those are the angles, and the lowercase c is the lengths. So for here, I know that means I have the length of A and B and the angle of A, and I'm looking to get the length of C. So that's because the law of sines is this equation, sine of A over A, sine of B over B equals the sine of C. They're all equal. So you kind of have to fill in the blanks, and any side that has at least 3 out of the 4 values filled in, then you can rearrange the equation to get the final. So you have to use algebra. You're gonna have to like move equations around. So that's really kind of like the gist of it. You just take this equation, fill in everything you know, and any equal side. So like let's say if I know A, B, and sine B, or like angle B, but I don't know any, like I only know 1 C over here. So if this side has 3 out of the 4, then this is the side I use. If let's say I know 3 over here, 3 on this side, like B and C like stuff, then I do that. If I only know A and C stuff, then I just do that. Just ignore it because they're all equal. So and then just you solve the equation, and then you get the, once you solve the equation. So let's say I have A and like the 2 A's and the 2 C's. Now I have them finally full. Like I got the fourth one. So now that I have the fourth one, I can probably then use it to solve the other. Like I said, once you have the 2 angles, that means the middle angle will now be whatever is subtract, like A plus C minus 180. So now you have this angle. So then you can use the equation to get the final thing. So like I said, once you get 2 angles, then you can get the law of sine. So if you're new to laws of sine, that's kind of like the gist of how you can go about using it. So yeah. Like I said, I don't remember where the angle's coming from. I forget. Let's see. I'm not testing for 4. I'm actually colliding. So so let's see. To collision. So I take the sphere's position and resting position and to collide. So the what position of collision? Like how far the colliding sphere is, basically. Where's the colliding sphere currently? Or not? No, this is by vertices. I'm checking every vertex in the shader. So resting position. Okay, I'm testing to see how far the resting position of the vertex is away from the center of the sphere that's coming to collide with it. That's to collide. Then this way I get the length. So how far is the vertex is away from the sphere? If the vertex is inside the sphere, like it's colliding, it's either touching it or is inside of it. If it's less than, that means there's a collision. It should be test for sphere collision. So I normalize the direction based on the ball center and the sphere center. So I know the direction I'm going in. Normalized direction of vertex to collider center. So the direction from the vertex to the center. So from the vertex to the center. So I'm getting that direction. And let's see. Dot product of the direction A and dot B if the vertex is aligned to the center of both circles. Oh, so if it's like dead center. So if the vertex is like right here, dead center, I don't need to do law of sines because that dead center spot is the radius of the sphere. So it's a condition. It's like, why bother do the law of sines when I can guess where it is? Because if it's dead center, so if it has this value, then it's like dead center. If it doesn't, I'll solve the angle of B. So, oh, okay, that's where the angle is. Because I know from here to here, from this point to this point, I know that line, and I know the direction of this line. So this whole yellow line, I know that angle right here. The angle where this actual point is, that's where the angles come from. I just couldn't remember. That's right. So this line plus this line, get the angle between this one. So this way I can then solve for this length. Ta-da. So once I looked at the code, I'll know where the angle's from. I didn't realize it till now. So once I know the angle, I pass in the angle, I pass in the radius and the collider length. And then I get back my length of C, and then now I know the length. So I have the direction of A that I'm trying to get to times the length that I want to go, plus the resting position and the end. And that is my new position. And then, of course, we have to say velocity. If it's not colliding, run the physics. And so if I go to the second one, so here's a sphere, and you can see that these points are exactly where they need to be. And actually set this up so I can kind of control it. And you can see the vertices, when I let go, they kind of shake. So if I press and then I press the down button, so I can just move the sphere out of the way and just release it so it stops colliding. So I can just move it, boom. So now I have a collision, and I have it also animating. I can just animate it. Boing. So, and I can just drive right through. And then the other side has a little bit of collision that they got hit. And there you go. And like I said, in the true sense of poke Abby, I am poking a mesh, and I'm creating an impression into the mesh. And then when I let go of my pressing into it, everything on them shifts back. So this is really now you're starting to get like soft body physics. Now you're kind of like trying to mimic a little bit of Jello and flesh. You know, now we're really cooking it here, right? So this is kind of cool, right? And on top of this, it's running all on the GPU, right? This is really cool. I love it. This is like, think about it. Like, I did this all on my own because there's like really nothing out there to really teach you this. So it's kind of funny. Like, I did have help. I can't remember who told me. Because I was having problems trying to figure out the triangles, and someone told me use a law of sines. You have enough information for this set of equations to solve the problem. You know, and because I've used a law of cosines before, I never really used a law of sines. So, you know, I never went to college, so I never was taught math. Actually, no, this is probably what taught me. I don't know if this was taught me in high school. Maybe it was, but I don't remember. I did pre-calculus in high school. That's as far as I got. So I probably did do the law of sines and cosines. Don't know. So there we go. We got a little bit of... Now, moving points around is not really that much fun, right? Like I said, you know, I keep advertising this Poke Abby thing. And no, I'm not going to go to Poke Abby. Again, if you're under 21... don't Google it. Don't. I'm probably going to get flagged, and I'm worried I'm probably going to get screwed for this video. So this video is going to disappear from the internet because I'm keep mentioning that word. All right, so since we're not going to poke Abby, we're going to poke Vegeta because the Princess Saiyan loves to get poked, right? So it's really the same thing. The previous example, this is really the exact same thing. Let's see. I think it's not that much of a difference. There's just... versus... Yeah, it's the same thing. It's almost... I probably did a few small different things. Smooth step. But yeah, I'm still doing collisions. from vertices onto a sphere. Actually, no, I shouldn't say that. I'm not using spheres for collisions. I'm actually, well, I am, but I'm gonna poke it with a ray intersect, and I'm gonna find out which triangle my ray intersects, and then once I know which triangle in the mesh the ray intersects, once I do that, I know the point on the mesh. So at that point, I'm gonna say, well, a sphere hit me there. I don't know what size of the sphere. I don't know. U radius. So it's the sphere is like that. That's the radius of the sphere. So I have it built. I have the hit strength too. I don't know what that means. Oh, how hard? Yeah, because it's like I'm poking. So I wanted to kind of simulate like how much. And the most interesting thing is I can keep poking at Vegeta, and the springs get worse and worse. It kind of builds up. I build it so it builds up. So, so the spring movement keeps being built up, which is kind of cool. Like I said, and like I said, this is it. This is really all to it. Like it's just this chunk of code. Transfer feedback is what does most of the work. And like this part we've been doing for like ever. So now if I start poking Vegeta, I poke them in the chest and it kind of vibrates. But if I can keep poking at it, it kind of like it builds up. It builds up all that energy. It's like because in Dragon Ball Z they do these like rapid punches. So it's like here's Cell beating the hell out of him, and you have all these blah blah blah. Everything's all jellified. Croc shot. Boing. Whoa! Poke Abby. I think Vegeta went and looked up Poke Abby. Don't tell Bulma. So, yeah, there you go. Why not? Poke his butt. Saiyan butt. So, there you go. Fun. I probably can make the sphere bigger, too. And I can probably... Well, not. Let's try it out, because I don't know what the hell. I'm going to do... Say 4. It's going to be 4 times bigger. Boom. That's a big hit. Bong, 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 bong. Oh, so much. So I'd say it's basically Jello. I've seen a couple of tutorials about like Jello, and I don't know, they do it differently because Unity gives you so much. So with this, you have to build that thing from scratch. So while you're building, you can be a little bit more creative. But yeah, there you go. It's not like how wobbly his arms got. Like I said, I haven't really played with these settings, so maybe I did. Let me see what strength is. I don't know. I forget. Oh, it's just real one hit, just boom, boom, boom. All right, let's have some fun. This is gonna be a big hit. Pow. Oh. There you go. Now we get some really jelly. We got a Saiyan jelly. And I know when I'm hitting, it's coming out. I did build it that way because if I build it like shooting in first, so when I hit, it goes in. I think that's why it's negative. If I were to do positive, that means I'm pushing forward. You get a different effect. Oh, it's kind of hard to tell now because now it's all massive. Let's do. I think the strength was 3 originally. So it's hard as it presses in. So when I'm doing negative, when I hit it, it's actually springing out first and then springing in. But now with the positive, it springs in then springs out. Because I think it was more noticeable the other way. I don't know. It's pretty noticeable too. So I want to go back to making this gigantic. So the sphere, when I hit it, is going to be... Vegeta is 1.67 meters tall. I think I made him to scale. Well, I didn't make the mesh, mind you. I just resized it so he's to scale. So yeah, I'm gonna do a full body, I'm going to hit him with as much, with a ball as big as him. It's not as much fun. 0.5. So it's a pretty big ball. I gotta use right clicks. Oh, hey, that's kind of funny. Jig, 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 jig. Boing, boing. There you go. That's cool. That's why I never really. Let's give it a lot of strength. There you go. Like I said, it's kind of cool because you can move, all the vertices and kind of everything kind of builds up. And there you go. Spring physics. Like I said, we're playing with flesh, so small numbers.